Okay, so in this problem, we're constructing the influence line for the shear at C, and that C is right here in the center. So let's imagine that I'm making some cut here at C. Do you have a particular side you want to work on? Yeah, why not? Let's do the left side. So when we look at our free body diagram, we'll want to go this way. So I'll have a reaction at A that I need to deal with first. Then, of course, over here there'd be a reaction at B. We're not really concerned about that. So the first thing I need to do before I can cut the structure and look at the internal shear, since I'm working the left-hand side, I need to find the reaction at A. So this problem is going to require me to find the influence line for AY just to get started. So let's do that first. So what I'm going to do is I'll draw again my free body diagram. I'll put my unit load at some distance x from the left. And I've got AY and BY. Now, how am I going to find AY? How would you normally find AY? Probably some moments about B, right? So let's do that. So I'll use right-hand rule for my sign convention, and I will sum the moments about B. Make sure it's in equilibrium. The first thing you'll notice is, I forgot the dimensions here. The first thing you'll notice is that what's this distance? Since I'm summing at B, it's going to be the length 12 minus x. So this will be 12 minus x. So about B, the moment due to the unit load has this moment arm, 12 minus x, and it is positive. So I'll have 1, there's my force, and 12 minus x is the moment arm. So that accounts for this. And then I'll have AY, which is creating negative moment, and then I'll have a moment arm of 12. So we'll solve for AY, and AY is equal to, looks like 12 minus x over 12. I guess we could rewrite that if we wanted to 1 minus x over 12. That might be a little easier to deal with. Does that make sense? So at x equals 0, what's AY? Looks like 1. Does it make sense that AY would be 1 when the load is sitting right here? That does. And as you move away, all the way to B, which is at 12, x equals 12, this is 0, AY goes to 0. So it's linear. Okay, so now I have AY. Let's actually find the influence line for the shear at C. So the first case I'm going to look at is when my unit load is between 0 and 3. That means it's on the free body that we're drawing. So let me draw that free body diagram. I'll have my unit load. Remember, we're always measuring x from the left, and this little piece is 3 meters. We know AY. AY is equal to 1 minus x over 12. And then I'm looking for the internal shear at C. How do I find the shear at C? Oh, I probably should go ahead and add this. Even though we're not looking for it, there would be a moment at C. So if I'm interested in just the shear at C, how do I find that? How do we normally find vertical forces? We sum forces in the y direction. So let's do that. So assuming up is positive, I'll sum forces in the y direction. So with up being positive, this force is down. What about this force? Down. And then this force is up. 1 minus x over 12. Everybody see that? Did I leave anything off? So what is the shear at C? Looks like the 1's cancel, and you just get minus x over 12. This equation is only good from when the position of the load is 0 to 3. What happens when it goes from 3 to 12? Well, let's see. So between 3 and 12, I have the same free body diagram. There's my segment of the beam, 3 feet long. I still have my reaction at A, which is 1 minus x over 12. I still have my shear at C and my moment if I was looking for it. Just like we found the shear force by summing forces, we're going to do the same thing here. So if I sum forces in the y direction, make sure it's in equilibrium, what do I have? Well, I have shear acting down, and I have AY acting up. So when that's the shear at C. So when I solve for the shear at C, what do I get? 1 plus x over 12. Oh, I said plus, didn't I? I messed up. It should be minus, right? Sorry. You see the difference between these two? So this is the position of the live load. That means the live load is somewhere between 0 and 3. Now this is the position of the live load, somewhere between 3 and 12. Well, if that's true, it's not on this section of the body. It's on the right side. So let's plot that and see what we got. I didn't leave myself much room. I'll stick it up here. So here's the shear at C, function of x, and I'm going to, there's the length of the beam, and there's 3. So this will be the value from 0 to 3, and then from 3 to 12. So from 0 to 3, I'm plotting this curve. So when I plot this curve, at x equals 0, I get 0. At x equals 3, what do I get? Minus 3/12, which is what? 1/4. So this is minus 1/4. And then I switch over to my other equation that's valid from 3 to 12. So I put in x equals 3 here. What do I get? I get 1 minus 3/12, which is 9/12, and 9/12 is 3/4. So this is 3/4. And then let's go ahead and push it all the way to 12. At x equals 12, it's 1 minus 1 is 0. So I get this. And then we can go ahead and connect those. So I get this kind of sawtooth looking thing. So where's the maximum shear at C? Where do I go stand to create the maximum shear at C? Well, the biggest ordinate value is what? 3/4. And that would be just to the right of C. Because just to the left at C, I'm creating a negative shear of what quarter? Then I step just over C, and it jumps up to positive 3/4. And again, if I weigh 200 pounds, what's the shear? It'd be 3/4 of my 200 pounds, 150 pounds. While we're here, I want to show you something kind of interesting. What's the change in shear equal to? 1. That's going to be super handy later on. This change as you step over the point is always going to be a change of 1. And why is it 1? Well, the load is 1. So we can use this help later to help us maybe come up with a shortcut. Any questions about that? Sorry, my elbow got in there. See it? Okay, I'll stop.